So just a refresher, we know that SQL tells you what you're going to get. You write SQL to specify what the system is going to give you. You don't tell it anything at all about how it's going to give you that. So, what has to happen, obviously, is that you fire your SQL off at your database management system, and the DBMS says, oh, look, I've just received some SQL, I've got to do something with it, I'm going to have to translate this in various ways to get the results specified in this SQL. So, the thing that does it is called the query processor or query optimizer, depending on which bit of literature you read, one or the other, usually query processor. And obviously doing this efficiently is pretty critical. You think what database management systems are used to do. If the DBMS can't do its query processing decently, then it'll run like treacle and will not be very useful to anybody for anything. So this is, if you like, within the database management system, it's trying to figure out how best to do things. So we're trying to minimize the cost of executing queries. So the overview of this process, okay, so we start with a calculus query on the conceptual schema, in other words, some SQL. And we decompose that, we bring in the conceptual schema, we turn that into an algebraic query. So first of all, we take our relational calculus, SQL, and turn it into some sort of relational algebra representation. We then say we're going to optimize this, and so we reorganize the query. And what we do, we take details of the physical schema, so we know what files we've got, what file organizations we've got, how big they are, how selective our predicates are, all that sort of thing. So you've got physical schema and statistics. So if you look deep in the bowels of any DBMS, you'll find that it maintains tables of histograms which tell it roughly how selective various things are. On average, how many of these relate to something else? How frequent are these values? What's the distribution of these things? And those are the things that it uses to do its query processing. So, the optimization module says, all right, we will reorganize this query into something that's reasonably efficient, then we'll go and execute it, and at the execution stage, we bring in the arguments. Now, what you can see here is that you've got this division between the compile time and the run time. So, if in some systems, most notably DB2, but you can, and also if you use the SQL in Java, the prepare statement, so that says, go away, DBMS, think about how you're going to do this, because I'm telling you that we're going to do this a lot of times. Okay, whereas if you're just constructing some string of SQL on the fly, you know, the DBMS assumes that you're going to do it once. So it says, all right, let's do this reasonably quickly, get a reasonably efficient plan out, and get it done. If you know you're going to execute the query a million times, it's worth putting quite a lot more effort into this compile time phase. Okay, so what difference? Why is it hard? Why is it? Okay, so the issue starts in that there is no algebraically polynomial time type efficient way of calculating the best plan. The only way we can find the best plan for any query is to calculate all the costs of every possible plan. That obviously is essentially combinatorial in the number of relations, and there's some things for intermediate results as well. So that gets hard. So what we want to do is to find some heuristics which will enable us to get a good plan quickly. Okay. Now, what we try and do, the approximation here is, for query processing, we say the cost function that we're trying to minimize is the size of intermediate results, hence the statistics. So, an example. All right, so fairly familiar. Select employee name, employee department, department manager from employees and departments where the employee department works and the department name is the same and the employee salary is under 40,000. Right, so if we've got 1,000 employees, 100 of whom are earning more than 40,000, 30 departments, and we will assume that our cost is proportional to the size of intermediate results. Right, so the first thing we could do is, so I have to sort of read this from inside out. So we're doing a join on our employees and departments with an equality on department name. Hang on, yeah, that's right. And then a restriction on that to get those three out, and then we're doing a projection on that. Okay, so what do we do? So the first thing we do is we get 1,000 by 30 for the join. We then do the restriction and projection to get our 100. So our execution time is proportional to 30,100. You might think this might be all right. On the other hand, if you think that's a small little bit of database, you think, maybe not quite so bright. Can we do better? So, yes, we take the same query, we reorganize it, and we say, let's do the restriction first before the join. So we're doing the restriction. It's the salary greater than 40,000. Then we're doing the join with the department on that that restricted bit, and we're doing the projection afterwards. So what happens? Okay, so the restriction gives us 100. This is good. And the join with department gives us 100 again. So it gives us about 200. 200 as opposed to 30,000. That's a big win. So it makes a big difference. Sorry, sir. Right.
Case against them. Trying to get rid of it, it keeps coming towards.
Oh, right, I see. That's right. Yes, you only want to sign it once. I can quite understand that. So I was just catching the grimace, you see. Okay, so what we can see is there are big wins to be had in making our queries behave efficiently. And it's hard. So what are we doing? Right. So what do we have to take into account? We have to take into account, all right, the number of organisations, speed of disks, we have memory available, CPU speed. So there's a whole bunch of hardware stuff. And databases don't always respond to, let's chuck some more hardware at it, as well as you think they ought to. Okay. That is quite difficult for the query processor to take into account. We can do things elsewhere to take that sort of thing into account. Right, what we can do is database organisation. So what's the logical design, what's the record size, what's the file organisation, what secondary indexes are there, all that sort of stuff. So this is stuff that the DBMS knows and it can take into account. Okay, and how many records there are. Obviously, as database designers, database administrators, we've got control over what we're doing here. But we'll look at that a bit later on. Now, okay. So how complex are our database operations? That's the next thing. So there's a bunch of stuff we're going to take into account, and then what are we going to do? So, all right, so if we do restriction and projection, restriction, so this is, we just reducing the number of tuples that we're looking at. So processing one tuple doesn't affect any others. It either meets the criteria or it doesn't, or will accept rejection. So that the efficiency of a restriction is simply cardinality of the relation being worked on. That's easy, number of records, great. Projection, right, if we're not eliminating duplicates, then, so in other words, we're doing just select, not select distinct, then also it's proportional to the cardinality of the relation. If we are eliminating duplicates, then we've got to do a sort as well. So, so R log R, and N log N type operation. And that will dominate. Now, join. Join, it depends what you do. We'll look at join algorithms in a bit. But if you said it's roughly in the cardinality of the relations involved, that's about right. Okay, and Cartesian product is an R squared, or N squared. Okay, so obviously, can we possibly avoid Cartesian products? We really don't want them. And if you, yeah, most of you must have made the mistake by now of doing a join and forgetting to put the condition in. Yes? And you've seen it go bang, and you get thousands of records everywhere. No? Yes? Yeah, okay. You do that once and you think, made a mistake there. Right, so Cartesian product, really bad. Join and projection with duplicate elimination. You don't want to do them on big things if you can avoid it. Restriction, that's just on how big things are. So, what do we want to do? Right, obviously, right, okay, so, what we try and do is, we could, as I said earlier, take a combinatorial approach to find the optimal design. We don't. What we do, we try and do several things. First of all, we look for duplicate sub-expressions in our query. So if we've got duplicate sub-expressions, that means we're evaluating the same thing twice. So what we want to do is only evaluate that thing once, whatever it happens to be. And again, what you have to think of here is some really big queries that are doing joins over several or tens of tables and using quite complex criteria. So, we eliminate duplicate sub-expressions. We try and do restriction and projection first, because that's a good way of reducing the size of intermediate relations. And then we order our binary operations over mostly our joins, but this also applies to union and so on, to minimize the size of intermediate relations. And then if we've got an operation with several algorithms, again typically a join, we say which is our best algorithm given the indexes and sizes of things that we've got. Now, if we're being really clever, we look at a whole workload and try and optimize that. It's too difficult. We can't do it. So let's give up on that. Now, when do we optimize? We'd either do it statically. So if we're doing our optimization statically, we are relying heavily on the statistics, because otherwise we can't determine the intermediate results. And we're doing our optimization once for many instances of a query. If the database organization changes, then we have to recompile the query. Right. We could do it dynamically, so at each step we look at what, we take the first step, we do it, we look and see what's the best thing to do next, given what else we've got to do, and just do it step at a time, step at a time. Now, that's at one level nice because we know the size of intermediate results, and we can be exact there. At another level, it is not nice because we're having to think about each step. Right? If we've done it here, we can just say go, press the button. We don't have to do any comparisons, anything other than the brute processing required for the database, for the query. So, if we're running it lots, this is great. If we know we're only running once, this is pretty good. In practice, what most systems do is a hybrid approach. So they do a static approach, and then they compare the results they're getting from the query with the plan. And if there's a big difference, they'll start thinking again. It's more complex, but it works pretty well because it's really saying, we've got a plan, is it working, is it working? And if it's working reasonably well, you don't do anything. But if it suddenly starts going badly wrong, then you start intervene, you do something else. The other thing that you do with this is you compile, and Postgres and most other systems do this. You compile a query, and you remember the plan, you stuff it away somewhere, so if by chance somebody runs the same query again, you say, I've seen that one before in this session, I'll go and pull it out and save home to replan. Okay, so it's doing that secretly without telling you. Right, so we're trying to decompose our query. What do we do? The first thing is we say, have we got legal SQL? So we do some lexical analysis, and then we do some syntactic analysis. Do all the objects referred to exist? Do the types match? And so on. So what we're trying to do is to find a way here of saying, user, you got it wrong. This isn't legal SQL. This refers to things we haven't got. Have it back again. I don't have to do any work. So that's that first phase. Assuming you've got legal SQL, which refers to things that exist, you can then go on to normalize it. So you translate it, you compile it into relational algebra, and you rewrite it in normalized form, usually disjunctive form, because disjunctive forms of relational algebra are easier to break into subqueries and join things up again by unions. Okay, so it's just the algebraic manipulation gets easier. And the other thing third thing you try and do at that stage is to see if the query is self-contradictory or incorrect in some way, because again, if you can reject it and say, no, this doesn't make sense, then you don't actually have to do the work to show that it doesn't make sense, but your analysis shows it. Having done that, the next thing you try and do is to simplify it. So if we've got multiple criteria which actually replicate each other in effect, then we can, so on redundant, we can get rid of them. We did do some things on some of the subgraphs, again using some heuristics to make them more easily computable, and we apply some integrity rules to see what effect they're going to have, and get, hopefully you end up with a simpler query. At the end of that, you can then say, right, now we're going to restructure our query. So we transform the program, the relational algebra, into a tree, and we can shuffle things around on the tree using some equivalence rules. This is just a convenient way of reorganizing things, if you like. So we have a leaf representing. No, I'm not going to go into it. So I haven't got enough. Basically, I haven't got enough time. Right. Now, what we're trying to do in this is to reorder the operations, decide which indexes and so on to use, which access paths, choosing by some appropriate algorithm. Now, our statistics tell us the selectivity, and the optimizer will then go and use the relational algebra for statistics to generate several plans, and we'll select the cheapest one. Okay. Now, usually what you try and do here is you're not going to explore the whole space, so you just look at the joins, which are usually the most expensive operations. Right, now, our query restructuring. This is the core of it. This is what makes query optimizers clever, that they can reorganize and restructure the queries. So, joins are commutative. So in other words, it doesn't matter which order you do a series of joins in, you get the same result at the end. That's good. So you can reorder a series of joins any way you like. They're commutative, so it doesn't matter which way around you specify the relations. It doesn't matter which way, in which order you do them. Okay. Again, you can do a separate set of restrictions, and it will have the same effect as doing those restrictions all together. So you can group restrictions quite happily. You can commute restriction and projection. So again, you can change the order of those quite happily, and you'll still have the same result. Okay, so we've got some more rules. So we have another 3 rules. Right, join followed by restriction is equal to restriction followed by join. So in other words, you can push those around in either order, you still get the same results. Projection and join, you can do the same. And that's assuming that the join attributes are in projection. Okay. And we can group projections together. So, essentially what it's saying is we've got a lot of freedom to reorganize a sequence of operations, to group operations together. Right. Okay. So what we usually try and do is push restrictions and projections before joins. Restrictions and projections usually get rid of more intermediate results. The cost we're trying to minimise is the size of intermediate result. So, if ideally we find some restriction or projection operation which gets rid of 90% of what we start with, and obviously that's the one you move right to the beginning, because at that stage you've got a small intermediate result, and everything else that follows from it will also be small. So, projection restriction reduces the size of intermediate results. Right, so what do we do? Typically, we will separate our restrictions with several predicates into a series of restrictions, each using a single predicate. So what we're going to do is to group our restrictions together. Then we're going to push them as far down the tree as possible, so do them as early as possible. And we're going to group sequences of them again. So essentially, we're going around picking up things with several predicates, getting them into one, grouping them, pushing them down until we can't do any more. Then we do the same sort of thing with projections, so push those down as well. We group them. Right. Oh, there we are. Oh, I've lost a slide, I think. Hang on. Yeah, sorry, I've lost a slide there. Okay, so we do that, and only then do we try and do the joins. Okay, so it's basically the last bit says go and do joins. Okay, so we're pushing selection, the restriction projection as early as we can in the query, holding on to the joins, where hopefully we've got the smaller intermediate relations, which are things we do with the more expensive operations. Right, so if we say in most systems join is the thing that makes the biggest difference to overall performance, then join algorithms become important. There are essentially 3 join algorithms. and you can reckon that every system implements them because they have advantages for different sorts of things. Right. You have to have nested loops. Nested loops is the only join algorithm which works regardless of any indexes, regardless of what file organisation you've got, and so on. Okay, so if there is nothing else, you can make nested loops work. So what you do, for each tuple in the outer relation, so that's usually the bigger one, you test it against each one in the inner relation and put it on the output if the two match. Okay? So you're going through the bigger thing once and the smaller thing, the inner thing, once for every tuple in the outer. Now if you think of our initial example where the outer relation would have 1,000 in it and the inner relation would have 30 in it, that's where your 30,000 comes from. You can go through all that lot. Okay. And obviously, if you did it the other way around, you use rather more memory. So you wouldn't. So you always put the smaller relation in the inner loop, in nested loops. Okay. So then we have sort merge. Sort merge is efficient on big things. If you've got something big, it probably pays you to do sort merge, even if they're not appropriately sorted, appropriately organised to start with, because you can figure that this is going to get expensive, really expensive, as you get into two fairly big relations. Whereas sort merge, sort both relations on the join attribute, and then just merge. So it's standard. Yeah, pretty much everybody should have seen one of these things before. At least anybody who did data structures and algorithms should be happy with that, yeah? Anybody else should be thinking, yeah, I can sort of see how it might work. Yes, you've got two things, you say, but is it bigger, so you're just stepping through. Okay, so that's logarithmic in the size of relations, so that's not bad. And third one we've got is a hash join. So it says, for our outer relation, construct a hash table, so run through it, hashing on the join attribute, and then for each tuple in the inner relation, hash and probe the outer relation for matching tuples. So if you've got if you know that your join key is unique, this is usually quite a good way of doing things, because you should get very few clashes in the hash key, and so it ought to be quite efficient. Right, okay, so here we go. I've talked about most of this. Yeah, it's brute force, it's horrid. Right. Okay, if you've got an index for nested loops, its performance improves. Okay, because rather than if your inner relation is indexed, then you're only searching the index, not searching the whole thing. So you've got less things to look at, smaller things to look at, using less memory or doing less I/O. That's good. Okay. Now, sort merge, we've talked about. Yeah. Okay. Right. Okay. So that's really what I wanted to say about query processing. So it's a very quick skate through. The basic lessons to take away are that what you're doing is turning a thing into relational algebra, manipulating that so that you do the restrictions and projections first, and you postpone doing joins as late as possible. When you're doing joins, you have to think quite well. The query processor has to think quite carefully about which join algorithm to use, and that's dependent on file organisation sizes and so on. Right. There we are. I skated through that decently.